So today, this is the Programmable Storage Workshop 1 session. As I mentioned earlier, we'll have a session 2 in the afternoon with some talks from Sam at Red Hat and Ismail on the new OSD work from Sam, and then from Ismail the scheduling. This is actually OSD level based scheduling, so those are more Ceph internals. And in this workshop, we're going to talk about some of the extensions with Skyhook and deployment methods, and then give an overview of that first. And today's first speaker will be Saloni. She worked with us here and finished her master's degree this year, as I mentioned. She worked on embedding WebAssembly into Ceph. So for the types of functionality that we've been talking about, selections and projections, those are the things we're offloading into the storage system, or in this case, the object storage system, using these Ceph extensions that we've developed. So importantly, for this session, we wanted to emphasize that Ceph has this extension framework. It's already there. We didn't have to add it. We just used it to do the thing we wanted, which is like database processing, for instance. So users can already write their own functions. You can compile those functions into a shared library, and those are distributed to Ceph storage servers. And then those functions can be applied by the storage servers to the local objects data. So in this context, now for Saloni's work, instead of compiling these functions in the Ceph shared object library, we can take something like the generic Ceph shared object library, which reads the data off of disk and then hands it to another completely independent code binary for processing. And that completely independent code would be something you might write in one of the languages supported by WebAssembly, and then compile down to WebAssembly, which is a binary format. And then that function is distributed to the storage servers. And then Ceph can do, as I mentioned, the generic extensions, kind of read local data, hand it off to this other processing method, and get the results back. And this other processing method is WebAssembly executables, and that's what Saloni is going to talk about today. So she graduated recently and then joined Amazon, and today she's going to talk about some of her master's thesis work. So please go ahead, Saloni.
Hi, I'll just quickly share my screen first.
And Saloni, before you get started, I just wanted to add, this is Stephanie here, that we're using the reminder to everyone that we're using the symposium minutes and not the chat for direct questions to presenters while they're speaking. I just dropped the link to that in the chat now. And if you do have questions for me or logistics questions, please go ahead and you can use the chat for that. But any other content questions, go to the minutes document. Thanks.
Okay.
I'll answer that too.
Just a second.
Let me open up the symposium minutes here, so if you guys have questions.
Can you see my screen?
Yeah, we do.
Yes.
Okay, so I'll get started. Hi, I'm Saloni. Today I'm going to talk about a project called Extending Ceph Objects to Support WebAssembly Executables. I was working on this project as my master's thesis, and I was advised by Jeff and Carlos. So if you're not already familiar with Ceph, it's a distributed, scalable, fault-tolerant system. It's an object store which is widely available in the cloud. So if you look at the architecture on the left, there are storage servers here where each server has a disk, memory, and CPU, and they're all connected in a network. So whenever you want to store something, each file is actually partitioned, and each of these partitions become objects. And then there's a data placement algorithm which decides how the data is actually placed across the storage servers. So objects are actually the key entity here. And then there are other API wrappers on top, like there's a file interface, block interface, and S3 interface. And then Librados is the core library underneath that interacts with those objects. So we generally use this Librados library that allows us to interact directly with the object. and let's just create user-defined object classes, and I'll talk about object classes soon. So programmable storage. A programmable storage system basically exposes internal subsystem abstract as interfaces. So current work on programmable storage has shown how to embed user-defined functions that perform data management tasks into an object storage system. So basically pushing down some tasks into the storage layer and thus allowing the storage system to provide application-specific functionality. So this ability to add user-defined functionality to the OSD is actually a very powerful feature, as it allows applications to reduce network round trips, data movements, and also exploit remote resources. Now, object classes in Ceph. So we've discussed that objects are actually the main entity in Ceph. So clients can directly access the objects managed by the OSDs directly rather than going through intermediate services. So Ceph can be extended by creating these object classes that define customized read and write functions. So the object class framework provides the mechanism such that each added function is compiled into a shared library, and that library can be loaded into the OSD process at runtime. So these added functions are generally written in C++, and then they are bundled as an object class. And there's usually one class per particular storage interface. So we'll talk about it in the future. There are quite a few, like a ref count, and then WebAssembly is another object class that we've added to Ceph. So the only problem here is that object classes are kind of closely tied with Ceph. So even though there's an SDK, updating the object class means adding new libraries and restarting the OSDs, which can be kind of disruptive to the user. And then restarting can also take a currently active OSD in a running cluster offline. So the current version of Ceph allows us to copy new libraries into a running Ceph cluster without restarting the OSD. But it's not a very reliable thing to do, and that's why we've basically tried to embed a WebAssembly in Ceph. Okay, the Skyhook data management project is another extension to Ceph. It is built on top of Ceph and provides storage layer extensions to Ceph by leveraging the programmable storage capability. So Skyhook enables data management tasks to be directly offloaded directly on the objects in the storage layer. So the tabular data is actually partitioned and then stored in these objects, and various SQL operations can then be performed on the data for processing, such as select, project, and indexing. So Skyhook also supports transforming data between row and columnar formats, and the data management functionality is provided through the object class mechanism that we talked about. So Skyhook partitions relational tables by row column, and then each partition is mapped to a corresponding object in Ceph. So tabular is actually one such object class that allows SkyhookDM to offload these data management tasks. So in the project that I did, we use Skyhook as a demonstration example for WebAssembly. So this is the basic architecture for Skyhook. And today the object class mechanism is used by Ceph file system to push down computation to make POSIX IO requests faster. And you can read more about it in the Amalgalogy paper. So let's talk about what WebAssembly actually is. So WebAssembly is a binary format that promises near-native performance for web applications. So it's a new type of code that can be run in the web browser and has many advantages like performance and security. So it is a compilation target for sources like C and C++, Rust, etc. So developers don't actually write WebAssembly directly, but they write it in the language of their own choice, which is then compiled into a WebAssembly bytecode. So the bytecode is the version binary and is then run on the client. Generally, it's the web browser where it's like translated into native machine code and executed at high speed. So till date, only JavaScript was supported, and now WebAssembly has support too in the browser. So WebAssembly also provides like a sandbox execution model, which is based on the same security models that exist for JavaScript. And so WebAssembly actually had huge implications for the web in particular. It provided a way to run code written in any language and then could be run in the browser at near native speed. Today, all major browsers, Chrome, Firefox, Safari, and Edge support WebAssembly executables. So, okay. So normally what you do for any language is write your code. Let's say you're writing your code in C, compile it using GCC, and you get an object file, which is essentially a binary file. So the primary use case of WebAssembly was to take an existing C program and then enable it to be run on the browser. Now to generate a WebAssembly file, you can write your code in a language of your choice, compile it using a specific compiler, which is unscripted. There have been a few more compilers these days, but then this is the most popular one. And here again, you get an HTML file and a WASM module, which then can be run directly in the browser. And it instantiates the WASM in order to be executed in the browser. Okay. Okay. While WebAssembly was designed to be run on the web, it was also desirable for it to be able to execute well in other environments, including shells and servers and IoT devices, and maybe even desktop and mobile apps. So there are many use cases even outside the web. So I know that Cloudflare has been actively using WebAssembly to run some code with minimal overhead. And then there have been quite a few developments, even for scripting languages and video games. So in order to enable running a WebAssembly program in a non-web environment, there has been quite a lot of development. And these non-web environments is what is called as a WebAssembly runtime environment. So after some research, we reduced the most prominent options currently available. And those were running the code either in a virtual machine, which is the WAVM, which actually stands for WebAssembly Virtual Machine, or running them through a runtime library. So Wasmer was the most famous one and quite developed. So both these frameworks have pros and cons of their own. We'll discuss them in the next slide. So since we wanted to leverage the features of WASM in Ceph, we performed various experiments to find which of the environments was better suited to our use case. So initially, we measured the overhead of using each of these engines, and we decided to pick two functions. One was a no-op function, which did nothing and just returned 0. And the other had like a huge counter, which took some time to run and then returned a value. So we considered every possible scenario, that is compiled code to both a C object file and a WebAssembly file. We then ran the C object file natively on the system and then compared its performance to the runtimes in both the VM and using the library. And it was observed that WebAssembly performed much better when executed using a runtime library over a virtual machine, as you can see here. These two and here. Also, we considered a few other factors that the library could be easily integrated with Ceph, but also the size of the WebAssembly binary file that was obtained was very small compared to VM. The only advantage that the VM had over the library was, since the VM ran in its own sandbox environment, it was a lot more secure. So to embed WebAssembly in Ceph, we leverage the capabilities of programmable storage and the non-web runtime environments, which in our case was the library. And this entailed implementing WASM as an object class in Ceph. So our object class just had the library API call. So now the main driver to run the WebAssembly file was already on the OSD in Ceph. So the user could then write their own function, compile it to WebAssembly, and distribute it to the OSDs, which could be injected at runtime. So then the client could then just simply call the function with the required parameters and execute the function on the data in the OSD. So initially we tested very trivial functions. My WebAssembly binary, which I had placed in the OSD, had very simple math operations, and I just called the function from the client, and the function would get executed on the data. But we wanted to test the performance of WebAssembly in a real world scenario. So we picked an existing processing function in tabular Skyhook, which was written in C++. Let's call this function F. We translated this data processing function to WebAssembly, and this function actually processed tabular data in the flat buffer format. A similar function had existed that processed tabular data in arrow format. So the need for processing different data formats provided us the motivation to actually build a common interface that allowed processing functions for new data formats to be injected dynamically. So this function was chosen in particular since it involved processing different data types within WebAssembly. So I think it iterated over rows and then called a filter function to apply predicates to the flat buffer data. And after processing, the rows that passed were added to a flat buffer builder, which was then sent back to the client. So we deployed a library to have the necessary framework to execute a binary and compile the processing function F to binary, and then placed it on the OSD and measured the performance of how the query performed when it was written in C++ and in WebAssembly. And generally, as you can see, the native performance was much better, but the experiments were performed with approximately 20 rows of data. So more experiments need to be actually performed with a larger data set. Which brings me to the limitations and some of the problems we faced while implementing this. So the WebAssembly implementation supports C and C++ primary data types. It does not support more complex data types such as vectors and flat buffer objects. So as a workaround, we first had to cast any non-primary type into a primary data type and then pass these buffers to the WebAssembly code. So it was kind of difficult to share an address space where both the calling function and the processing wasm binary function could write to, because the whole point of WebAssembly was that it was supposed to be sandbox, but here we were talking about sharing memory. So our use case required us to be able to provide the wasm binary with access to the object data. And initially we made several attempts to declare a shared memory buffer, but it was actually violating the whole sandbox boundaries. So the current implementation allows passing an address that is read-only for the WebAssembly process. So in order to get past the limitation of sharing memory, we declared the result buffer memory location to be global in tabular, so that both the functions could actually access it. Since we kind of violated the sandbox boundary a bit, it is a security risk. And so the current implementation of WebAssembly takes as input a function name, the name of the runtime environment. So our current implementation has both the running it on the virtual machine and the library. And we also take function arguments. So it is assumed that the binary file is present on the OSD server, because when we were performing our experiments, we had to copy this file manually to the OSD. It is actually important to implement a dynamic method and possibly like a function repository so that the Ceph OSDs can retrieve these binaries themselves on demand. So our implementation also follows the blueprint of Lua. So previous extensions to Ceph with Lua had shown that a method could be executed dynamically, but it was only with interpreted Lua programs. And so basically it was platform independent, but it wasn't language independent, and that's what we are trying to achieve with WebAssembly. And like I mentioned previously, we need to perform the test with a much larger data set to actually see how WebAssembly performs. And that's it.
Thanks, Saloni. Maybe if you want to leave your slides up for a minute, just in case you have questions. So maybe I was going to ask if there's any questions. I have a few we can talk about. I was hoping to be a little bit interactive, like I said in this session. Since there's a lot of different options for programmable storage or computational storage that people are familiar with, and these are just some of the ways that we've been able to exploit that notion in Ceph with the object class extensions that Saloni mentioned. So one thing that I think was interesting during your work was the rapid development and all the time actually it took to find a usable WebAssembly library.
Yes, we did have a lot of issues with that because it was difficult to find versions that were actually compatible. And yeah, so it was, I mean, some of the WebAssembly files just supported older versions of scripting, so they didn't even compile correctly. And then the runtime couldn't actually execute the WebAssembly. So version compatibility should definitely took a lot of time.
And for people who might wonder about the security, so the WASM VM, or yeah, I guess that's right. The VM version, right, is sandboxed and all of that. And maybe, Saloni, if you could talk a little bit about how that might be different or might not be different from the current way that we register shared libraries in Ceph, which is really just distribute them to OSDs, right? Is it like, what security benefits do you think that offers? Is it just memory corruption, isolation of that kind of effect, or what? Can you talk a bit about how it might differ if we use the VM versus the library?
So the VM is actually like any other VM. So it has its own environment and it's completely sandboxed. So sharing memory there was almost impossible. There'd be a lot of violation there. Like the memory had to be completely outside of the VM and the program then if we had used the VM. So, but with library, somewhat, since we were embedding the library completely inside our Ceph code, it was actually possible to, I mean, access the memory there. But definitely if you're using a VM just to run simple programs, like maybe outside of Ceph, then it would be much better to use a VM because it's completely secure then.
I think there was two problems with the VM, like, well, two considerations, right? One is just the startup overhead of the VM. That was.
Oh, even that too. Yeah. So if you look at the graphs here, maybe.
As well as like the time you'd have to copy all the memory.
Yeah. If you see the difference here, then this was almost 3 seconds, while this was just 0.03 seconds if you used a library. So the VM took a lot of time to actually instantiate a WASM module because it was all self-contained and had to do everything by itself. So there was like a huge difference. Sorry.
That's the pure overhead because this is a no-op function. So that was the cost to start up the VM and call this no-op function essentially, right?
Yes, yeah. So this was the native, so this was our baseline. So 0.0042 is what you would get if you were executing a simple C object file. And then compare it to WebAssembly, then that's 0.03. But then if you actually put it in a VM, then it explodes to 3 seconds. So if there's a lot more data, it would probably take a lot of time to actually execute. So it didn't really feel like a very feasible option at the time.
Right, and then the graph on the right-hand side, right, is the same function, right? Same function. It's copying any data, you're just like doing a computational function locally. So I guess there's the fixed overhead you can see like from 3.3 with the Wasmer library to 4.8.
Yeah.
But that doesn't include copying data into it. Like we have to copy.
No.
Right, so that's the
Mhm.
again. So I guess it would depend on how much data you'd have to copy as well.
Yes.
And so what do you think are next steps for that then? Do you have any quick next steps?
I did actually do some research over it, and then there has been some development recently. And I think the libraries are more evolved, and then everybody has been talking about the memory issue. And I think WASMA actually is working on it currently, and maybe we should have something about it soon.
Okay. So there might be other students interested in picking up this work. If you are, let me know. I know Jian-Chen had mentioned a little bit about that and WebAssembly and some other different maybe approaches, but definitely think it's an interesting area to continue to explore.
Yeah, I'm aware that like the WebAssembly, they trying to create standardize the web interface and standardize the system interface besides just the web interface, so that allow the WebAssembly binary code to call the system call, the kernel system call. For example, you can open the file and write file outside of sandbox, something like that. I think this is exactly the trend the WebAssembly community would like to push forward the scope out of the browser, but also can access some resources on the system.
Oh, I remember looking for this, if there was a way to actually write to a file because of the whole memory issue. But then at the time when I was working on it, there was no development on it. But good to know that we can do that now.
Yeah. And some people say, because the web interface is, the system interface is called WASI, the WebAssembly
System interface, yeah.
Yes. And that people say, if WASI plus Watson was born earlier than Docker, and then probably Docker won't exist because they already
Oh,
create a sandbox environment and pretty skilled, just like Docker container.
yeah. I think I read about it. It was pretty interesting.
And so one last thing for people wondering, or if you have questions, just please ask. It's not necessarily a Ceph-specific solution, right? So we should emphasize that especially like the WebAssembly approach that she investigated here. I think this would apply like to any storage system or object storage system, at least with our current design, that allows you to extend functions on objects, right? So if you have that same functionality that Ceph has, where you can do partial read and writes of objects, and you can extend an object functionality, essentially create your own, read or write method. It's basically what we're doing. Then you could create a method that reads the data as normal and then just hands it off to this WASM VM or whatever, and then gets it back, right? So that's sort of the ladder scaffolding that you need. It's a pretty small amount, but if you had that, right, you could apply this WebAssembly generic, there's a little bit more generic solution maybe than some of our compiled Skyhook libraries that target, a Ceph version. This is just simply any object storage that lets you read data, pass it off to a processing method and get it back, and maybe consider the security boundaries, obviously. Then this is kind of a more maybe a more generic approach, right, to injecting new functionality into storage system. Which is part of the goal of this workshop. So. Mm-hmm. And if there's any other questions before we move to Jayjeet? Okay. Okay, well, thanks again, Saloni.
Thank you.
You're welcome. Thanks for your presentation. And now if Jayjeet is on, we can switch over. Hi, Jayjeet.
Hi. Shall I start?
Sure, if you want to share your screen, I can give you a quick introduction.
Okay.
So is an undergraduate student at NIT Durgapur. And he comes to us across here through the IRIS-HEP project, which is a multi-year NSF funded software innovation for research in software for high energy physics. These are partners of ours on this particular Skype project. And they analyze CERN data So they have a lot of analysts, many of whom use Python. They have a lot of libraries, and they have a very strong, robust community. So they actually provided fellowships, and Jayjeet is one of our Iris Hub fellows. And his goal here was to work on a reproducible way to both deploy and benchmark Skyhook in the large and small. So this is a good thing for our project because it allows us to do both reproducible experiments, but as well as, make deployment much easier for people into the different types of bare metal or existing clusters. So today he's going to talk to us about his work that he did on that through his Iris Hub fellowship. Okay, Jayjeet, thank you.
Thanks, Jeff.
Sure.
Yeah, I hope my screen is visible and I am audible.
Yes.
So, yeah. Hello, everyone. My name is Jayjeet Chakraborty, and I am currently a senior year student at NIT Durgapur in India. So I came across Cruz last year during my Google Summer of Code. So I worked there on reproducibility, and then recently through Iris Hub, I dived into storage, and this project is kind of a bridge between reproducibility and storage systems. So yeah, this project was mentored by Carlos, Ivo, and Jeff. Yeah, so this is the talk outline. So first we'll discuss the problem and our solution. Then we will see our reproducible workflows with Popper for experimenting with Ceph and SkyhookDM. Then we will study a case study that we did for finding bottlenecks and overheads in SkyhookDM on a Kubernetes deployment. And lastly, I want to leave you with a short demo on expanding the scope of the talk to how to get started very quickly with experimenting on a complex storage system such as level DB. So, okay. Yeah. So the problem in doing systems experiment, like the problem in starting with systems experiment is that when someone starts experimenting with systems, basically storage systems, they need to first boot up infrastructure for deploying the storage system. That can be in the form of virtual machines or bare metal nodes. Then they have to build and deploy the system on that cluster or the standalone machine, if that is, and then run experiments iteratively on that, and then finally download results and generate plots and notebooks for sharing the work. So what is generally seen is that these steps are kind of differentiated from each other, so they need to be done separately, and that involves a lot of manual work, from typing in a lot of commands to boot up nodes on any cloud service, or building and compiling and running experiments, writing Python code to plot the results, etc. So they may be automated in their by themselves in the three categories, but no one but there is not a framework to do all the things together, just running a single workflow or executing a single command. So yeah, so one of the problems that comes with installing a lot of tools and experimenting with storage systems, large storage systems, is that they have researchers need to install a lot of tools and dependencies, libraries, build tools, etc., and that increases the overhead and increases chances of errors because of outdated versions or stuff like that. So to solve that outdated dependencies or versions problem, what we can do is containerize the commands or scripts and share them in the form of several Docker build and Docker run commands in a README with someone to reproduce. So each command will look something like this. Like this is a run benchmark script. Someone might, so it will also have like deploy in the context of say deploy Ceph. Then first will build Ceph, then deploy Ceph, then run benchmarks, then plot results. Each would have a Docker run command for them. Although it tackles the problem of installing a lot of software and the platform dependency problem, but with as experiments get large, the number of Docker run commands and the number of flags to pass to each command and the care to be taken to run each command also increases in complexity. So that does not quite solve the problem of getting errors. So this needs automation. So yeah, before talking about how to do the automation, we described the tool that helps us to automate the containerized steps, which is Popper. So as containers abstract on operating systems, similarly Popper abstracts on containers. It allows you to, it abstracts container engines, different container engines for different use cases, like Docker, Singularity, which is used in HPC, in Slum clusters, etc. Podman for rootless environments, and also it also abstracts tools like CI services like Travis, Circle CI, etc. So it might not be clear what it does. So let me go to the next step. So with Popper, it is the ideology behind Popper is to have a is to have a format as close to as a bash script, but inside a bash script, each command runs on your local machine. But what we want is run each command or script inside a specific container. So you define a series of steps where each step consists of the image, the container image that has the required dependencies and the software, and the commands to run inside a container made from that image. So so this way you can, instead of providing a README full of Docker run commands, you can provide a YAML file, which is a Popper workflow file, with the steps declared in that, along with their container images, and that and the user, as you can see on the left, the user has to just clone the Docker file, or clone the repository with the Popper workflow and run the Popper run command, and all the steps will get executed one by one. So yeah. So how does that framework help in automating or containerizing SkyhookDM experimentation workflow? So SkyhookDM has a lot of not like every software has a lot of documentation, guides from building and deploying and running benchmarks and queries. So for someone getting started with Ceph or SkyhookDM, that might be a bit overwhelming and can increase the time before they could just get a view of how it looks like. So what we did is we took each granular step of a SkyhookDM exploration workflow, like deploying infrastructure in form of Kubernetes clusters, deploying Skyhook or Ceph, they're running benchmarks, then running queries on Skyhook. So we prepared Popper workflow files for each of those granular steps, and basically converted the entirety of the documentation and guides into 6 or 7 Popper run commands, and anyone getting started would just clone our repository and run these commands in order one by one to have an entire SkyhookDM experimentation reproduced in front of themselves, without even knowing the intricate details of it. So that would just help in getting started faster. Yeah, so that was kind of introduction to my work, and now I will show how it looks like in real. So again before that, I will briefly describe Ceph, what is Ceph, and what is Ceph and SkyhookDM. So first Ceph. So Ceph is a object storage system that provides three types of interfaces for file access. One is file system interface, one is object interface, and one is block storage interface. The most striking thing about Ceph is that it has no central point of failure. It has an algorithm called Crush that maps objects to OSDs and sends that Crush map to every client that connects to a Ceph cluster. In that way, it avoids having to query a single server every time for the location of the objects, and every client that connects to a cluster can generate the location by themselves and directly connect to the OSD. So it makes it highly scalable to the level of exabytes. And what is more important is that for SkyhookDM is that Ceph is highly extensible through plugins. So it allows programmable storage. So it provides you the Rados API for interacting with the cluster, and provides a object class interface, which can be programmed in an ad hoc manner to operate on the data that is stored in Ceph in the form of objects. So what is SkyhookDM? So SkyhookDM originates from Ceph. It uses that object class interface of Ceph to write plugins in C++ that is used for data management and data query inside the storage layer. So what it adds is it allows storing large tabular data sets in objects, and allows pushing down operations like selection, projection, aggregate, like basic SQL operations to the storage layer, and allows querying the data inside the storage rather than on the client side. And in that way, it avoids a lot of overhead in transporting the entire data back to the client just for the purpose of querying. And yeah, it also supports querying two orientations of data. One is row-based flat buffers, and another is column-based Apache Arrow data. Yeah, so now that we know about Ceph and SkyhookDM, let's see how to build and deploy Ceph on bare metal, or on bare metal, basically on VMs or bare metal nodes from Cloud Lab. I guess that the term bare metal is a misnomer there. Sorry for that. Okay, so if you are deploying Ceph on virtual machines or bare metal nodes, first is the build step. Without Popper, you need to first pull the repository, check out the correct branch, run the CMake commands, build the binaries basically, and use tools like so that is up to build. So you have to use CMake, make, and a lot of commands like that, and the scripts that are provided in the Ceph or same in the Skyhook repository. But with Popper, how it helps is it puts these exact similar commands in the form of scripts that are containerized. So you can see the Git pull step is containerized inside an Alpine Git image, and that prevents you from thinking about installing Git or the version of Git, and the builds and the scripts for building Skyhook is inside a build script that uses a builder image, Skyhook builder image, that basically builds Skyhook from its source code. So when you have a workflow like this, you can just run the workflow or the two steps of the workflow. One is and one is init, that is to clone the repository, and is build. So with two commands, you are done building Skyhook on your machine or anywhere, without having to go through all the steps that are given in the documentation. Yeah. So after you're done building Ceph or Skyhook, I will tell Ceph or Skyhook most of the times, because most of the steps are very similar. So please don't confuse with that. And yeah, so after building, so the next comes deploying. So again, we consider doing manually first. You have to use you have to use tools, DevOps tools like Ansible, Puppet, Terraform, or Ceph deploy to deploy Ceph on a cluster of nodes. That again comes with the overhead of managing configuration files, playbooks, looking at readmes, learning a bit more about these tools, and increases the overhead basically. But with Popper, we can automate the same exact steps, and we can put all the required files, playbooks or configuration files in a GitHub repository, and orchestrate that with the help of a single workflow file. That would have a step starting with deploying Ansible. That would have a step starting with using Ansible to deploy Skyhook on a set of nodes. Then it would have a step for going into SSHing into each of the nodes using Ansible to copy the Skyhook libraries into the Ceph clusters. So basically, it will orchestrate the entire thing for you, and you do not need to think about. You do not even need to look into the configuration files or the playbooks or the scripts, and you can start without learning about Ansible Terraform. But you will be using it underneath. Okay, so yeah, this was for deploying on a set of VMs or a set of nodes, and now I will be talking about how deploying Ceph or Skyhook on Kubernetes makes the process even easier. So why Kubernetes? And why Rook? So the de facto way currently for deploying Ceph on Kubernetes is using the storage orchestrator Rook, that basically utilizes all the capabilities of Kubernetes, like easy version upgrades, rollbacks, self-scaling, disaster recovery, and applies them on storage systems. So yeah, so that makes storage systems like Ceph, like batteries included, and it also allows using since it is a Kubernetes environment, you can use tools from there are a lot of tools in the Kubernetes ecosystem that have operators, so you can get operators for almost anything you want to do, and just makes your workflow quite easier. Yeah, so for deploying Ceph on Kubernetes using Rook, you need to build a Ceph Docker image that will be handed over to Rook, and Rook will take care of deploying and starting the proper daemons like the managers, mons, and OSDs in the cluster. So the thing starts from having a workflow that builds the Ceph image, that clones the Ceph repository, builds it, generates a Docker image, run tests, and push that image to a remote repository that can be called by Kubernetes for deploying in a Rook cluster. So that can be called by Rook for deploying in a Kubernetes cluster. So you can see the workflow here. It first builds it first builds Ceph and then packs into a Docker image. Packs it into a Docker image, and yeah. So after you have built Ceph inside Docker and created a Docker image for it, the next step is deploying the cluster using Rook. So with Rook, for the basic four configuration files that needs to be applied for deploying Ceph with Rook is these four: the common.yaml that deploys the namespaces, the RBACs, etc. The operator that deploys the Rook operator, which basically is a watcher over the entire cluster and sees what is going down, what version is getting upgraded or downgraded, things like that. Then is the cluster that deploys the OSDs and mons, and a toolbox for connecting to, that basically provides a set of tools for connecting the cluster. But yeah, still this might look fairly easier. But if you want to do if you want to have a lot of customization while deploying Ceph with Rook, you will end up probably with a lot more configuration files than these four. And also you need to run them in the correct order. Otherwise, like in Kubernetes, if something goes out of order and things hang in the terminating state, then it is a really pain. So if we can even make this easier with Popper. With Popper, we can make a step and declare and use a kubectl image to run the kubectl apply commands in proper order. So if you have the workflow, you do not need to think about on which order to run. You just clone the repository and run the corresponding step, and Popper will take care of that. Yeah, let's look at a demo quickly. So I am running the setup step command, setup Ceph step. You can see the image is pulled, the kubectl image is pulled, and one by one the namespaces, the file systems operator will be created. Yeah, if you do not use Popper, you have to do these things manually, one by one, in the proper order. That can be error prone. So you just run the Popper run command and sit back. I hope you get an idea. I will not spend much time on this. This will finish. So after you have Ceph deployed, the step I showed was for deploying vanilla Ceph, like the Ceph Nautilus version. So after you have Ceph deployed, you might for experimenting with Ceph, the step that comes inevitably is making changes to the Ceph source code, or making changes to an customization of Ceph like Skyhook, and deploying it repeatedly multiple times to test, to benchmark basically. So you need to upgrade the cluster multiple times iteratively. So for now, coming specific to Skyhook has a tabular class, has a so this is the C++ object class that uses the object class SDK that Ceph provides, and this code handles all the querying and projection of the data by querying the data from the objects. So so this shared object file goes into each of the OSDs, and each OSDs need to be restarted for this shared object file to take effect. And so manually, if you do this, you need to, using any tools or manually, you have to SSH into each of the OSDs and put the libraries in the correct places, in the correct directory basically. So yeah, so this is upgrading Ceph to SkyhookDM manually. You have to follow a script like this in a loop. You have to in a loop SSH into each of the OSDs and place the libraries in the proper location. And also you have to upgrade the Ceph config to load the classes. So this again becomes manual. And you have to restart the OSDs again. So to avoid this, we can directly use to avoid this. Rook helps us to avoid this basically. So as we have seen this step to deploy a vanilla Ceph version. After we have built the Skyhook Ceph version also in the similar manner in the workflows that we saw few slides back. After you can just run this deploy Skyhook step, deploy Skyhook Ceph, and it will automatically upgrade each of the daemons to use Skyhook Ceph version without you have to doing anything. It will inject the. It will apply the new Ceph config, and also the new the Skyhook Ceph image will already have these shared libraries inside it. So this makes it very easy. Just you make changes, you make changes to Skyhook, you build the Skyhook image and run this step. So it is like make changes, pop-out run, build Skyhook, pop-out run, deploy Skyhook, and that's it. You can iterate on that. I hope it plays. Yeah, so let's convert a Ceph cluster to a Skyhook cluster. As you can see here that there is no libcls tabular in that list of libraries. So we know it is a vanilla Ceph cluster. Now we are upgrading it to Skyhook Ceph.
Jayjeet, where is this Kubernetes cluster running?
You mean this right one on the demo?
Yes.
Oh, this is in Cloud Lab.
Okay.
That I did, yeah. So yeah, so you can see some one second, yeah. So you can see some activity here. It detects the upgradation of the version of Ceph to Skyhook, and it will start upgrading each of its daemons to Skyhook. So now you can see. So after it has finished upgrading, I try to execute ls command inside the old OSD, and it is not found. That means that old OSD is crept up and a new OSD has come into action with the new SkyhookDM, with the SkyhookDM image. So cluster updated that, and now I find out the new OSD, select a new OSD from the list of OSDs that I have, and I try to find out whether there is a libcls tabular in that OSD, in the proper path in that OSD, in the LD library path. So yes, it is. So we can tell that, yeah, the cluster has been successfully upgraded to Skyhook from vanilla Ceph. Now that you are done with building and deploying, and you have two pop-out run commands to do that iteratively. Now comes the important step. The most important step is the experimentation. So with Skyhook, with pop-out, you follow a logical workflow similar to this. You first deploy infrastructure in form of a Kubernetes cluster. So I have just shown it in short. Then you build Skyhook image, push Skyhook image, deploy Skyhook, run queries. Again you follow the same loop. And our workflows help to scale the experiments very easily. So that's again inside another demo, how to scale the experiments after you have started experimenting. So currently it shows it has, so this is a workflow that runs queries on the Skyhook cluster. It runs queries on a set of tabular on a tabular data set that is present inside the that has been put into the cluster, and this workflow is used to run queries on the data set. So for the first case, it is a fairly small scale experiment with only 10 objects. We have put 10 objects, like we will put 10 objects iteratively into the cluster and query on them so that it is faster. So you can see the object count is 10. It will, the workflow, I run the workflow. The workflow starts, deploys the pods. You can see it will start inputting the data, inputting the tabular data in the objects. So you can see it has put 10 objects and it will run queries on them now. So I'm skipping it, this video a bit too long. It will run queries. I hope that's it. Okay. So now we ran queries on a small set of data, and then just by changing this variable inside the workflow, I will make it, I guess I did it 1000. Yeah. So by increasing the number of objects and the size of the data set, we seamlessly scaled up the experiment. And now we do the same thing again. Yeah, so you can see it put 1000 objects there, and it will run the queries again on the scaled data set. The speed is similar to that of the 10 because I have edited out a lot of slow parts from this. Yeah, so that's kind of a demo. How can you just change the parameters and run the workflow multiple times to scale your experiments. Okay. After the experiments are done, the step that comes is plotting the results inside notebooks and sharing. So we want to make the entire workflow reproducible, and yeah, we want to make the entire workflow reproducible. So we would again use Docker, but with Docker to run notebooks, it again takes a lot of flags and makes the thing complex again. So with Popper, we can again put all these commands inside a workflow and boil it down to a simple plot result step. That on doing Popper run plot, it will run the notebook and read the results from the JSON files that has been generated while running the experiments inside the workspace and plot the results. So Popper takes care of all the error-prone components, even while making notebooks. Again, our demo, I will do it quickly. So Popper. So yeah, so this is how to use Popper, how to run notebooks interactively with Popper. So you can run a Popper sh command and go inside the Docker container and run a notebook. That notebook is running inside a Docker container, but you do not need to think of the flags that you need to provide. So yeah, you do not need to think of installing the dependencies, and you just run the notebook without any problem. So the notebooks are self-contained and coupled with the workflows. Next part is finding bottlenecks and overheads in storage systems. Like how did we find out bottlenecks and overheads in a SkyhookDM storage system?
Hey,
So
Jay,
we have, yeah.
Maybe try to wrap it up in the next few minutes.
Yeah, sure. Sorry.
That's okay. I can shorten some of my talk there so you can get through yours and some questions. But yeah, we should wrap it up soon if you can, please.
Yeah. Sorry. Okay. So there's a three-step approach for finding overheads and bottlenecks. So first, you baseline the underlying infrastructure, the underlying hardware in terms of disk or network. Then you deploy an application, the vanilla version of an software, and find out its performance on that particular infrastructure. Then you make customizations to that application and compile and deploy it in loop and find overhead each time and optimize accordingly. Yeah, so these are some results from our benchmarking the UCSC River SSL cluster from benchmarking SkyhookDM performance on the UCSC River SSL cluster. So yeah, the disk had a bandwidth of 400 megabytes per second. The underlying block devices, the link speed was 8.8 to 8.5 gigabits per second bandwidth. Then we deployed vanilla Ceph on that, and we found that the peak throughput of a single OSD deployed on a single block device was less than 400 megabytes per second, and that is assumed due to the sorry for that. Yeah, so very sorry for that. That less than 400 megabytes per second was assumed due to the blue stores overhead. Then we scaled out the Ceph cluster to 5 OSDs, from 1 to 5 OSDs, and we observed bottleneck shifting from storage to the network. And then we deployed SkyhookDM, updated the Ceph cluster to SkyhookDM, and ran benchmarks on 220 gigabytes of data with 750 millions of rows. And we observed huge improvements in query performance from pushing down operations to the storage for the 1 and 10% queries, which is what we intended to have. And yeah, so what I discussed. Okay, so Jeff, can you give me 5 minutes, 4 or 5 minutes, if you have?
Sure, yeah, go ahead.
Yeah, sure. So I want to leave you guys with a small demo on how to get started with a complex software system like LevelDB using Popper very quickly. So okay, so I will quickly shift to my terminal. Can you see my terminal, everyone? Nice. Okay. Yeah. My terminal is visible. Sorry.
I don't see that.
No. Okay.
I don't
okay. I guess. I think now it will be. Is it?
Yes.
Okay. Thank you. Yeah. So I will go inside this demo folder. There's nothing now. So
maybe we should wrap up because Jeff is only 20 minutes rather than 30.
Okay, I see. Okay then. Okay, sure. So I would like to thank everyone from Cruz, Ivo, Jeff, Carlos for helping me on this project. And yeah, this was a really great learning experience for me, especially this was my introduction to storage systems. And if you have any questions about my work, please feel free to ask any questions or contact me on my Twitter handle. And I will share the link for the LevelDB reproducible for the LevelDB workflow with you in the Slack channel and in the Zoom chat. You can have a look and ask any questions you might have on that. And yeah, I would wrap up with that. Thank you everyone for attending this talk.
Thanks, Jayjeet. And thanks, Ivo. He did all the mentoring for Jayjeet, really. So we really appreciate that. Ivo's the expert on poppers, of course, as well. I don't see any questions in the document. Do people have any questions you want to ask live? No? So one point I just wanted to highlight with Jayjeet's work too is that how he mentioned, and to get a short demo, how to redeploy Skyhook into a vanilla Ceph cluster, excuse me, which looks equivalent to redeploying Skyhook if it's been updated into a vanilla Ceph cluster or one where Skyhook already exists. So it's I think a nice framework in this context for programmable storage of how to update such functionality, right, with the easy kind of redistribution of function method, which is essentially the workflow that installs Skyhook extensions to Ceph. Is that right, Jayjeet?
Yeah.
Yeah.
True.
Yeah. I think that makes it's kind of nice to redeploy and extend functionality in this way, which is what I kind of mentioned before. and what I like about this work a lot as well. Okay. Well, thanks again, Jayjeet.
Thank you. Thank you,
Hold on.
everyone.
Yeah, what a lot of work that he's done. So let me move on to the next talk. So it'll be me, and I'll share my screen here and give some summaries of Skyhook and some overviews for people, as well as some details for implementation. In the interest of time, what I can do is, let me share my screen first.
Sorry, Jeff, again for overshooting my slot.
That's okay. Let me see if this is the right one, I think. Did you guys see that? Can you guys see my screen okay?
Yes.
Yes.
Very good. Okay, so like I said, in the interest of time, we have about maybe 15, 20 minutes here. Maybe I'll talk a little bit about, are people interested in some of the CLS interface details or more of the physical design layout details with Skyhook? I'm not sure. Does anyone have a preference? CLS interface would be how you'd write your own functions and some of the details of how we did it. Okay, well, I can cover that, I suppose. I think that's pretty interesting. The programmable storage aspect for this group. So then let me make sure I didn't hide those slides real quick. Okay, so I'm Jeff, and I am Incubator Fellow here at Cross, leading the Skyhook project that we've been talking about some of the different approaches to it today. Skyhook is open source, of course. It's built on Ceph, as we all know. And today we'll talk a little bit about the computational storage nature of this. And we like to say that it's extensible and scalable and generic, right? So extensible because Ceph has its extensibility capabilities, it's already built in. It's scalable because we inherit the scalability properties from Ceph, since we just use their object level extensions that we create on our own. And generic, we like to keep it generic in this way, at least at this point, as a good example of generic computational storage. And by generic, I mean the functionality that we're using. For instance, we look at these formats like Google Flat Buffers or Apache Arrow. Those are open source generic formats. They're widely used. In fact, Apache Arrow uses Google Flat Buffers internally for some things. And generic being that if we can embed Arrow data into the storage as well as Arrow functionality that's built in, right, then that kind of keeps us in the space of more generic rather than like a one-off approach that only sort of solves this problem for maybe particular database or particular application or particular file format, of which there are many of those solutions, right? In the wild, there's a lot of these solutions that are sort of highly tuned for certain types of applications and databases. But this, we're going to try to keep it generic, and that's what I just mean by this. So some of this will be some from the SDC slides. So some of you guys might have seen some of this before, but I adapted them for this talk a bit. So computational storage, right? We can think of it as hardware, software devices, even network devices. A lot of talk about inline compression or transformations, data re-encoding, what you might want to do with computational storage functionality. And overall, typically the goal is reduce data movement right across a network. So if you can apply data reduction ops, such as compression, right, at the storage layer, then you can reduce the amount of data that has to be sent back to the client, right? And of course, many other operations are possible, some of which we'll talk about today, which are like data processing type things for database processing. Why we're doing this in Skyhook, right? So database machines is kind of an old concept, which was the notion of could we make storage system servers that would, act as a part of a component of a database, right? In the abstract description of that, right? And idea, today as well as moving computation to the data, right? This is a pretty standard principle these days. So you can think of this as we might want to scale out a single node client application. Like how would you scale that out? Usually, you could scale it up by putting on a bigger machine, but at some point you're going to have a hard time scaling out both IO and CPU. So how do we do that? Current approaches, you can have a MPP or massively parallel processing database, right? There's primary commercial solutions. There's also like Amazon S3. You can think of put these on a RAID array. You might put your database on a RAID array and you'll have IO scalability. And then some of these also offload some processing with S3 query and select, right? So there's some versions of this in many forms out there. It's a pretty popular topic for databases. Our approach we call programmable storage, and you can look at programmability.us. This is research from our lab here with the students and Carlos. And I describe it like to combine, expose, or extend existing storage services toward new functionality. Right, so why reinvent function at the client level if there's already that function in the storage level, but it's not exposed, right? Or you could augment it and expose it. So this is the approach that we take, and we do that specifically for in-storage execution of these data management tasks. We're going to do two things with that. One is dynamically offload, so traditional computational storage type idea, and also dynamically reorganize physical data configuration. And that refers to like the data layout, both across the system in storage and within a given object, right? How might we change the design or layout of that, whether we rotate it from, say, layout of row to column, or we insert some data into an index, like the RocksDB to create an index. That's what we'll talk about a bit. So those are the two focuses for the Skyhook approach. Those are critical for databases as well, so that's why we take these two main approaches. So next, I'll give a little example of the CLS interface that we keep talking about today, right? So this allows you to extend existing, it's an existing extension framework in Ceph that you can write your own classes and methods for objects, right? The methods are executed directly, and as we said earlier, like this is just shared libraries. So you just distribute them to the OSDs, like Jayjeet showed. You could just redistribute new shared library, right? Overwrite the last one. And this isn't like some sort of fringe functionality, right? It's actually core used by Ceph, for instance, CephFS, uses CLS, Rados Gateway, RVD. Many of these actually use CLS itself. So it's a core functionality, and it's a stable part of Ceph. This simply shows people are actually writing new classes and methods. So this is the count of classes and methods over time on the x-axis, and the count is on the y-axis, just to show that it actually is, you know, people are doing things that they want to do with this thing, with this capability. So when I talked earlier about, we don't want to say that our methods are specific to Ceph, although in this case they are, right? This is how we implemented. Any object store interface that allows these, that has these properties, right? So in Ceph, there's a chunk store. So you can think as writing extents to disk, so you can have broad device access. And also Ceph, there's a KV store. So you can read and write to the KV store. And we use this like for a localized indexing mechanism, right? But anything of that nature would be available. If anything of that nature is available in the system, right? We could take advantage of our techniques in the same exact way outside of Ceph in a different storage system, for instance, right? So for us, we want to keep track of where things are on disk, and we also want to store that with metadata. There's also Xadder interface, which you could query as well. It's not quite the same as being able to query a KV store interface, but those things are also possibilities if they're not, if the KV store isn't available. Again, not quite the same, but it gives you some metadata queryability. And the reason we need that is at runtime, at query time, by the time the query gets to the object, right, we might want to look up some information or some metadata. Some examples of this are read and write. Right? So as I said earlier, just previous slide, right, this chunk store. So this is read and write to the chunk store and offset and links. You can do partial reads and writes. There's metadata. You can set and attributes, just like there's X headers. And then you can also read and write keys and values to the local RocksDB. Right? So you can utilize that interface. Ceph just exposes these, right? So this is something that anyone can use. In our case, we put like metadata in there about like say indexes or column information or physical offsets for different pieces of tables. Right? So we just use it in the way that matches our use case. Importantly, like why might you want to have a system that has partial read writes of objects, right? So that's another property that we would need an object storage system to use a lot of this kind of functionality, or at least optimized for, right? If you have a table and an object, you might want to split it into subtables. And then why might you want to do that? Well, you might want to read part of that table, or if you have an index that says all the data you need is this in this part of the subtable, right? The subtable could be sets of rows, It could be sets of columns, right? So maybe column 1 and column 2, or maybe row group 1 and row group 2. All these kinds of things are possible when you can write to partial objects. Right? And then if you store that information in the RocksDB, this is exactly how we would use it, is it would keep track of where are those pieces or subsets stored, right? And that way at runtime, query time, you could look up where to go on disk to read just the subset you like that matches the query. So here's a real quick example of an actual CLS class, right? So on the left-hand side, this is C++ snippet of the Ceph CLS interface. So this is the thing that exists in Ceph. You just define your class and a handle. Sorry about the script font there, but you define your class and a handle, you create an initializer, and you register your method, right? And we're calling this method execute query op, right? And you register it as a read or write method. And we also have a method called build index, right? Or any other ones that you want to do. So for instance, for WebAssembly, right, you would say, you know, apply WebAssembly. And then you write that method, which is on the right-hand side, right? And this is your definition now. This is your actual function, right? So on the left, you define the classes and register their methods. And on the right-hand side, this is the function that you'd actually execute, right? So there's a query op. Inside the query op are the instructions. So notice this is the interface I mentioned that you need, or we would need for Skyhook to move into a different object store. Right, so there's a buffer input and a buffer output. And buffer list is just a set version of wrappable buffer. So in the input, right, we can serialize the instructions, for instance, select star from some table, right? So that you can think of as the query. And the output is going to be the result set, so the rows that match. And pretty much this is an exact example of such a method that you would want to do. So you decode that instructions into the op, extract the query information, for instance. You might look up that metadata, right? If you want to find out, apply these queries to subtables. Maybe you don't want to read the entire object off of disk at once into memory. So you can constrain that by reading, by looking at the metadata and reading the subtables in, applying the operation then to that process data. That's where you'd put your select and project methods, for instance. And then you just append the result to the output buffer. So that's kind of an end-to-end example of this extensibility framework in Ceph that we've used for Skyhook. And as I mentioned, this already exists, and this is not Ceph specific if you have these capabilities that I mentioned before. Okay, so a brief review of Skyhook architecture. People aren't familiar with it. On the bottom is Ceph OSDs, and they store objects. And the little blue things there or green things there are objects, right? And I think it's Saloni mentioned, right? Ceph handles object placement, right? We don't do that. We just name objects, give them to Ceph, and Ceph distributes them across a cluster, right? So the nice thing about this is, unlike some other systems that have to keep track of where everything is, we don't care where it is, right? We just know it's an object named something. We're going to name them in a generic way. And then Ceph will get them. We'll both read and write them for us to the right location. So that sort of location-based information is out of our hands and we need to manage it, which is nice. And then on each OSD, there's a little RocksDB parallelism, right? And your CPU parallelism is that method that we're going to execute, say, query op, because every little object is going to be able to use the resources on that OSD server. So you're offloading the computation to the storage in this case, and the parallelism comes from doing it on many objects at once. Right? And then, as I mentioned, right, this is multi-tenancy, right? So you can have two management applications running, A and B, both calling different classes and methods on different objects, for instance. In that respect, it's pretty flexible. And then real quick, let me cover partitioning and layout, and then just show you an example of how this actually does, in fact, offload computation and reduce network traffic. So partitioning, let's go to row partitioning here. So just consider an input table. Right now we take an Apache Arrow table as input. We format the partitions as little arrow tables, and we're going to store those partitions in objects. An important property is that the objects have to have the data semantics. So the key feature of programmable storage is having the storage perform operations, right, and do the operation in a declarative way, right? We want to have the object understand the data semantics, and that way you can apply these more declarative methods. In our case, object names are generated. As I mentioned, we don't want to keep track of all the maybe tens of thousands or millions of object names, so we can generate them in a simple regularized way and distribute it by Ceph so we don't have to store the object location. Types of processing we want to do, right? You think of select, which is row-based, project is column-based, aggregate is column-based grouping and sorting. These kinds of things are the types of operations we support. And as we move, which I'll talk about, toward the Arrow Compute API, right, we'll be able to support anything that the Compute API supports, right, including user-defined functions. Right? So Compute API supports user-defined functions, and you can apply that to data. So you can think of those arbitrary methods written by users. And this just says what are the kinds of metadata we might want to store. So we said physical location on disk for different partitions of tables. And we might want to store data such as indexes about what values are where, or what values live where, and what partitions, right? And the reason this would be done is because you can think of for database query planning, right? You might want to issue a index scan or a table scan. So these are sort of methods at the bottom of a query plan tree. You can think of that's how do they access the data or access path selection. So these are the kind of things that now instead of globally, right, each little object can decide on its own, if needed, right, to use its own index or to just do a scan of its local data, right? And that helps address things like data skew, where one object might have a lot of data from some value ranges and a different object may have a different distribution. So this is kind of what the benefits can be. Next, we think of when do we want to push down or not, right? So currently we just decide to push down, right, or not. But it could be a runtime decision, right? So we could always try to push down, and then the object, might decide that it can't do the operation because that storage server is overloaded, right? So we want to be able to have the ability to push back the operation and say, well, I'm just going to read the data, send it all back to you, right? And I'll let the client at that level do the processing. So that's something we can call pushback in this framework. And then I guess I can show briefly, let's just go over a picture of what a table might look like. So this is an arrow table format. So there's a schema and subsets of a sequence of record batches. And in this case, bringing back the earlier layout in an object, right? Why would we care about data layout? Well, it might look exactly like that. So for example, we might lay out the schema followed by a sequence of record batches, and then the RocksDB happens to know where each record batch starts and ends, for instance, and that allows us to sort of just read one at a time into memory and apply processing, right? Or read multiple of them, or go directly to the one that we happen to know. If we have an index, we happen to know that batch has the data that we want. Maybe the other batches don't. So all these things combined together are features of Ceph that exist that we exploit in this particular way that sort of help with data processing and offloading to storage. You can think of column-based layout as well, right? We might want to change this to layout columns in some order. And we can talk about transformations from row to column. This is just an example of that. So briefly, I just want to talk now about we're moving toward Arrow Dataset API, and then we'll try to wrap up with a quick result. So Dataset is a new API for Arrow. It's a big adaptation for our project. So it provides Arrow from end to end. So on the client side, you interact directly with an Arrow interface. And on the storage side, we've embedded Arrow tables, just like I've showed you already, into our query processing methods. So we both store Arrow on disk and return Arrow data to the client, and then the client can apply, the Dataset API can apply the functionality there, right? And the reason we're moving toward this with our project, right, Arrow is very popular. It's about strategically, right, this is a good move for us to try to get more adoption. Our partners are already users of Python and familiar with object stores and Parquet. At least Iris Step is one of the groups that we worked with, the ones to be one of our first big demos of Skyhook. And then it also provides code simplification because Arrow does apply, has its own select and project methods through this Compute API. And performance as well. Right? So over time, as we noticed, we were using Google Flat Buffers and Arrow, but every time Arrow would come up with a new version, right, the performance would actually increase. So and sometimes significantly so. So that we get some of that benefit because we just piggyback that benefit by adapting directly to using Arrow and get the benefits of their optimizations with new versions. And Arrow recently went to version 1.0 stable just during the summer. So this is why we're moving to that. And in to bring this back now to Skyhook, a data set is just a collection of fragments, which are really table partitions. A fragment is a schema and record batches, and similarly, so is an arrow table. So since we already know how to store and process arrow tables, now we can do that same functionality, but we'll do that as fragments in their framework. So to bring that back, the previous row partition looked like this, where these were arrow tables, and now we're going to wrap them in a thing called data set fragment. And these definitions are equivalent, really, so these are just sort of wrappers over tables. They're technically the wrappers over record patches, but that's what a table is. So I think it's a good change. It's a strong change for us, and it doesn't really fundamentally change the architecture, right? Our architecture nicely fits exactly this model. So we've interacted with the community, and we're developing a Librados, Ceph Librados fragment, right? So that's going to be read and write fragment in the Cephs. And that's the example, right? That's what was an arrow table. I bring that back from earlier. This is a data set fragment, right? So this is just a wrapper. Some examples are, you can see there's two columns, right? So that's a project query. That's the interface, the data set API. And there's a two table with a filter, a greater than equal to 7. So again, this is data set API. So we can get all those benefits without having to worry about writing that code ourselves. And we just apply them to fragments, which are the tables we already store on disk. Fragments define scan tasks, right? So there's columns for projections and expressions for selection. So that's the part that is part of the data set API that we're now adding. As Zhongfeng mentioned, we're adding to our storage system servers code for the CLS methods. Okay, and then lastly, does this work, or what happens? Does it really offload stuff? Does it help? Let me give a quick example of that. So consider a TPCH data set, typical database data set. We'll have split that table into 10,000 partitions. So there's 10,000 objects. We have flat buffers and arrow, different formats here, but we'll try to focus on arrow. And the queries are select and project on newer cloud lab hardware. And we'll just look at, if we start with this cluster with Ceph, with Skyhook extensions, do we push down or not, right? And we'll quickly show the examples of what is the benefit of offloading. For instance, for CPU, right? So if you consider a baseline query here, baseline read, no query, right? Just read all that table data and send it back to the client. Here's a picture of the CPU usage on the client and the server. So the server is actually, that's the CPU to read that data from disk on those 10,000 objects across 8 servers, and they're stacked there, and then send it back to the client. So the client is actually just receiving the packets in this case, right? So that's the actual cost to collect that data. So if we consider that a baseline, and then we want to apply a selection query, right? We'll do the same thing in storage, which is no push down. We'll just send the data back. And then you can see here the client is going to apply that select query. So that's that filter 1% of the rows. So the CPU on the client does go up a little bit because it's applying the filter, right? And then with Skyhook offloading on the bottom graph, right on the left-hand side, we can see this is the query over time. So that's and on the x-axis, and on the y-axis is CPU usage, right? And you can see that now on the client side, there's almost no CPU usage, and the storage side has gone up slightly, right? So we've offloaded that computation in fact to storage. It's spread across the 8 OSDs, and then the data coming back, you can see on the client side, there's almost no CPU % usage. That's because it's only receiving 1% of the data packets, right? So only 1% of the data is coming back. And so there's a lot of cost for packet handling, right? And that has an impact on memory, both on the server side and the client side, as you go through the media buffers and things, right? So this is the benefits that we can see, just as an example of CPU offloading, right? So I think we're kind of out of time, and that's the, basically the overview. And then last one, let's just say we have a query here, select extended price, so one column from a table. And on the y-axis is execution time for that query. And then there's 3 bars. There's row layout, right? And then on the left-hand side first, and in the middle, there's a column layout. So if we transform, like we said, physical data on every object, we'll lay it out in column format. That's the cost. And then we can see the little gray bar to the far right. That's if we lay it out columns independently on disk. Right? So in the middle bar, we're laying out columns as table, but a column-based format. And on the right-hand side, this is every column is set independently on disk. So with our RocksDB, we can look where it is, right? And just go look up exactly where that column starts, extended price in this case, and read just that column off of disk. So that's the IO savings actually that you see there. And that's how we can see the CPU is offloaded and the IO is actually reduced if we use some of these RocksDB tricks that we employ. So that I'd probably wrap it up there. Ongoing work with the dataset API and our acknowledgements. So I'll take questions for that and any questions you guys have about programmable storage or things you'd like to talk about. It's hard to rush through the end. If anybody has any questions about layout or anything?
What's your current progress with the Arrow integration?
It's actually going pretty well. Jayjeet has been and SMail have been working on the top client side, and they already have the storage side mocked out and the client functionality to, I think, read and send expressions. And then on the storage side, Zhongfeng has embedded the library, and we can now read and write fragments, but we didn't add the processing yet. And so that's going to be, we expect that to be done. We're on schedule for about the next 2 weeks here to finish that up. And the reason that's possible, right, is because we don't have to write all that code. We just have to unpack the serialized expression coming down from the client side. And once we decode that, we can apply it with the Arrow method. So we're on track for that over the next couple of weeks. And then we should have an end-to-end example of querying.
From a code size perspective, how big are the Arrow the Arrow things?
I don't. So lines of code, I don't know. We just import the libraries actually.
Yeah. How do you have any sense for what the memory requirements are or any of that kind of stuff?
No, I don't know.
Okay.
The layout though on disk, we can kind of try to restrict, right, the amount of data that goes in memory for processing at a time. But I don't know about the library size costs.
Okay.
We'll look that up. We can definitely look that up for you.
Yeah, I mean it's a question for if you have a device underneath of you that could do that processing for you, so that you didn't have to do it on the OSD server, but could actually push it even closer to the drive. What would be some of the memory requirements for pushing down that method library and utilizing it?
Yeah, that's a good question. So this would allow us to, if you had a device, you could do that with these different layouts, right? You could do that on a particular row or column, row group or column. But yeah, then you'd have to stick the library on there. I don't know, but I'll get that answer. Me and JG can probably look that up pretty quickly for you.
Yeah, it's definitely not an urgent thing. I'm just trying to understand, as we move down that path, what that's going to look like.
Mm-hmm.
I've got a question. Is there a natural way to throttle users so that you don't have one person on a shared cluster, so that if everybody starts using this and pounding our Ceph cluster, for example, are we going to have, is there a way to throttle it so that you don't overload the system with different requests from different users?
So you like access control at the client layer? I don't have that.
Well, I think at the server layer, say for example, the person is pounding it and doing heavy queries on the servers, and perhaps degrading performance for the rest of the users.
Right.
Is there a way to throttle these folks?
So the short-term answer, right, is this thing we're calling pushback, which is a server can reject the processing requests and just send back the data raw and let the top layer do the processing, which would look like a normal system. And the longer-term answer is SMail is working on, Yuming also is working on scheduling at the server layer. I think they'll talk a bit about this afternoon. And that might be a more direct way to, schedule information, schedule requests down at in the OSD itself, right? Once handed down to the OSD. So the short answer is immediately we can reject things. The longer answer is we're working on a more robust scheduling policy to do exactly what you said.
Good, thanks.
But yeah, check with this Mails Talk this afternoon. I think that'll hopefully answer some more questions or generate some more questions. Okay.
Right.
So I don't know if there's any more questions in the document. Let me know.
Right. And if there are, you know, if there are more questions that linger, aside from that, you have a second workshop coming up in the afternoon. There's also, of course, the Slack channel where people can throw questions up on, or the minutes. You can also do them after the fact and get answers from the author or the speakers at that point. So, well, thanks for everybody. Sorry for the little hiccup earlier with my computer kicking me off the internet all of a sudden. So we may have a slightly incomplete recording of this session or something that's tacked together with about a minute of missing a video, but I think we're okay. I just want to remind everybody, we will start back here at 1 p.m. Pacific time. So in a little over 50 minutes. And that will be with, we'll have our keynote for today, Spencer Sevilla, who is himself a UCSC PhD alumni, got his PhD from UCSC. And he's going to talk about challenges and opportunities in community cellular networks. And I think this is a particularly interesting talk. And I think I hope everyone will be able to attend. And if you need information on this one or any of the keynotes, those are actually on the website. You should be able to get the links from the symposium homepage for that if you want to read about them ahead of time. So with that, I think that's it from my end. I will stay on for a few more minutes, but we'll probably turn off the Zoom until after, till about 10 minutes prior to the next session. So anybody have any questions or comments or requests, let me know. Otherwise, have a good lunch.
Thanks, everyone.